So basically we are talking about ideal solutions. So we will also continue to do on ideal solutions, but more than one component. Okay. Now before we go to that, let us first discuss about something else which we did not cover earlier, which is the phase rule. Okay. Which basically discuss what will be basically the number of degrees of freedom, okay, in a system, and how it basically relates to the number of phases and the components. Okay. Now the first question first, what do you mean by the degree of freedom? Okay. A degree of freedom is basically the number of independent variables, right, that are required to completely specify the state of the system. We already discussed that. Suppose just take a gas, right? So the natural intensity variables are pressure, temperature, and volume, right? But these are connected by equation of state. So in general, we can choose any two of them. And since we are discussing everything in the framework of Gibbs free energy, the natural variables are pressure and temperature. Okay. So volume can be kept fixed, and we are just varying pressure and temperature. Okay. So in that sense, like total number of variables is 3, but the number is right here. The degree of freedom, which usually denoted as F, this is freedom, how many degrees of freedom are there, which is alternatively you can think as the number of independent variables. Okay, so that is basically 2. Now that is for what? That is for a bulk system. Now think about a different thing. Okay, the sound is coming. Like say something like this. Suppose I have a phase diagram. Okay. Now remember that when we are discussing what is this phase diagram, it's basically a plot of pressure and temperature, and it separates the regions of different phases, right? So this is a typical phase diagram, let's say for water. Okay. Now the question is, when we are here, let's say the liquid region. Okay. So I need actually 2 variables, pressure or temperature, pressure and temperature. Sorry. Okay. There are 3 variables, but of course these are connected. Okay. Similarly for vapor also I need, for vapor or for solid also I need 2, right? But what about the condition which are on the lines? Because remember, the lines are actually representing where the 2 phases are coexisting in equilibrium, right? So this line means, actually think about it, this line is an equation which is connecting pressure with temperature. Okay. So meaning, if I say that, okay fine, what is this point? Okay. So automatically this line, you will have an equation for pressure and temperature. That's what we derived. Okay. That is exactly what is the Clausius-Clapeyron equation, all these things. Right? So that we discuss. Now those are basically equations connecting pressure and temperature, which means actually you are reducing your variable further. Okay. To 1 instead of 2. Now we want to make this a generalized thing. Okay. Generalized thing in the sense that how many phases are present and how the degrees of freedom are connected to it. And not only that, this figure is for actually one component. This is for water. What will happen if I have water and phenol mixture? Okay. There are 2 components. Of course, then the degree of freedom will be dependent on 2 things. How many phases you have and how many basically components you have. Clear? Okay. Now from this thing, for one component it is very easy to understand. Like let's say one component. So when we have basically say the phases, okay. Let me just use the same notation. I think it is used as yeah. So I'm denoting the number of phases. Okay, that as P. Okay. Now suppose when I have just one phase, okay, what I said, the degree of freedom is 2. Already told, right? For bulk. Okay, any phase like liquid, solid, or whatever. Right. Now, when I'm here, like when basically the number of phases we are considering two phases are in equilibrium. Okay. You see here that if I have two phases, right, the independent variables are actually one because pressure and temperature are now connected. Okay. So I'll have basically one. Okay. If I had number of phases 3, where basically around this triple point, okay, then the degree of freedom is basically 0 because triple point is a very specific thing for a component. Okay. Let me give you one different way of thinking. Okay. I'm coming to that. So now you see that here I'm actually changing the phases. One phase means when I'm here, either liquid or vapor or in solid. Okay. Then the degrees of freedom I need two, temperature and pressure. Okay. Moment I am in the two phase region, meaning on one of these lines. Okay. Now pressure and temperature are connected by an equation. So if I define a specific value of pressure, temperature is automatically defined. So my variable is now 1, not 2. Okay. And when I have actually three phases here, this is just a point. This is already pressure and temperature is both specified. Clear? Okay. You see the nice thing here. If you add these two things, it is always 3. Okay. So you can readily say that okay, I can actually make a relation that this F, okay, is nothing but it is 3 minus P. This total is 3. Okay. But this is for one component system. Okay. And also it's not a general thing in the sense that this 3 is coming because actually there are 3 phases. Okay. I could have other phases, like I told you, like for water there are many exotic phases. Right? These are not only phases. There can be high pressure structures of ice and other things, right? So we want to make it a general thing. Okay. Now how do we make a general thing? And again, degree of freedom means actually how many independent variables you have, right? And then let us think that suppose I have 2 degrees of freedom, x and y. Okay. And suppose I have some equation, say x plus y equal to 3. Okay. So then how many independent variables I have? 1, right? Because if I just vary y, x is already fixed, or I can do it in the other way. Okay. But if I had actually 2 equations for 2 unknowns, okay, then I do not have any, I have a unique solution for x and y. Okay. So somehow, as you can see, this number of independent degrees of freedom, independent variables, or basically this degree of freedom, okay, is somehow connected to basically the number of variables, which in this case is 2, x and y, okay, minus what are the equations they are connected to? How many equations are there? Okay, so number of equations. Clear? Okay. So like as I said, like if I have only one equation, okay, I have basically 2 unknowns. 2 minus 1 is 1. One independent variable. Okay, in this case none of them are independent. However, if you see that I have suppose 2 variables, and if I have 3 equations, that is meaningless. Okay. The third equation should be already kind of defined. Meaning there is also this thing which you have studied, how many linearly independent equations are there. Okay, I'm not going into those details. So what I'm saying is that the number of equations can be maximum the number of variables itself. Okay, clear? So all we are going to do is to calculate this thing. What are the number of variables for a general case? Okay, and how many equations do we have? Clear? Okay. Now how to basically calculate it? It is again very easy. Okay. Now let us think about it. First calculate the first thing. What is the number of variables? All these variables, by the way, are intensive variables. Right? We are not talking about any extensive variable. Pressure, temperature, volume, all these things, right? Now suppose we do not have only one component. Okay, we have multiple components. So 2 variables are already there, temperature and pressure. You know that thing, right? So I have basically temperature and pressure, that will account for 2, right? But then I'm saying, suppose, okay, fine, I have temperature and pressure, but then suppose I have, suppose 7 components. Okay. Now the question is, or let's say, let's take a, easier example. Let's say I have 2 components, water and something. So let's say water and phenol. Okay. And suppose I have 3 phases. Now 3 phases means gas, liquid and vapor. So gas, liquid and solid. Okay. Now how many variables then I should have? See, for each component, okay, I'll have 3 phases, isn't it? Right? For each component. Now, for each component, I also have to define something known as composition. Okay. So, meaning what? How do you actually define what is the property of a system? One is temperature, one is pressure. Fine. But then you also have to define, okay, what is the mole fraction? Okay, something like that. Okay, that is related to the number of components, right? Now, suppose I have basically 2 things, water and phenol. So I'll basically need the mole fraction of water and phenol. Okay, but not only in just liquid. I need it for liquid, I need it for vapor, I need it for solid. Okay, so somehow what it basically telling us is, I will have, okay, the total number of components times the number of phases. That number, okay, will add more variables. Clear? Okay. What I am saying here is that, let's say, for example, I have, okay, so I'll just write the third thing, the components. Let's just write it at C. Okay. Again, let's say C equal to 2, meaning I have water and something, let's say phenol. Okay. Now suppose the phases, they exist as 3. Okay, I just took a mixture of water and phenol and I'm just varying the pressure and temperature. Okay. Now the question is, what are the variables here? Okay. Now again, I can vary pressure, I can vary temperature, I can vary the composition. I can vary the composition of phenol in all these 3 phases. Okay. I can similarly vary the composition of water in all these 3 phases. So total number of variables is basically 3 plus 3, which is 6. Okay, but this 6 is coming basically by 2 into 3. Because I have 2 components, I have 3 phases. Okay. That should be now added with this thing. Why? Because temperature and pressure were the fundamental variables. If you remember, what I am right now telling you is nothing but we are talking about the reduced energy variation, right? So I have VDP, I have SDT, and then I had mu I DNI. I am asking how many DNIs I have. As simple as that. Okay. Now for 2 components I'll have 2 DNIs, but there are 3 phases. Say alpha, beta and gamma. So I'll have a DNI alpha, DNI beta, DNI gamma. Okay. And for the other components, a DNJ alpha, DNJ beta, DNJ gamma. Okay. Yeah.
So but the mole fraction of both water and phenol will be related by the equation.
Exactly. So I'll make it as a constant that is related to the equations. First now I am calculating what are the total number of components. Then I'll put the number of equations which are basically reducing the number of independent variables. You are right. Okay, so this is the total thing, but these are not independent yet. So this is not the degree of freedom yet. Okay, I'm just calculating first the total thing. Okay. So naturally, everybody understood, right, what I'm saying? So I have pressure, temperature, and then I can actually make a generalization that if I have C component and if I have P phases, that will be basically C into P, as simple as that. Okay. So the total, what I'm getting is basically Cp plus 2, which is the total number of intensifiers. Maybe actually I should have showed. Okay. Now let us come to your question. Okay. How many equations are there? Okay. Which are connecting all these variables? Okay. What are these variables? One is pressure, one is temperature, and the other one is basically some relation between the components. Clear? Okay. So that we are now going to find. Okay. Now, first of all, there is this calculate the second thing. So we have here basically 2 plus C. Okay. Now the second thing, the way I have written is basically number of variables and number of equations. These are basically equations means how many like constants you have. Okay. Now think about it. What are the equations we'll have? Okay. So we'll have basically two things. One is when we are talking about like many components. Okay. For each component, I will actually have a mole fraction thing. Okay. Like for every phase. Okay. For all the components, I will have the total mole fraction should be equal to 1. That is one equation. Meaning, let me just write it. Like say, usually for components, okay, I write ij notation or 1, 2. Okay. And for say phases, we write usually alpha, beta, that kind of notation. Okay. So what I'm going to say is for alpha phase, okay, I'll have a relation like component mole fraction is x1, x2. Suppose I have C components, okay, those are connected. Okay, these are actually alpha phase. Clear? Similarly in beta phase also, okay, these mole fractions of all the components are connected. Okay, clear? So how many equations I will have is just equivalent to number of phases. Right? So each phase, the total mole fraction is equal to 1. Clear? Okay. So I'll have something like P equations, which is coming from the conservation of mole fraction. Okay, not conservation, basically the definition of mole fraction. Okay, for each phase. So those are basically equations. Okay. Now there is also a second thing. What is that? If the phases are in equilibrium, okay, then I'll have basically some equation like everything. You remember that it basically started the chemical potential in the alpha and beta phases are equal, right, at some pressure and temperature given the other variables constant. Okay, that's what we started all our Clausius-Clapeyron equation. Okay, or Clapeyron equation. Here in this case actually it will be not only pressure and temperature and also composition. Okay, but all the chemical potentials are equal. That is the equation when actually we have some phases are existing. Now this is basically equation of a line. Okay. For example, if 3 phases coexist, like the triple point. Okay. So I'll have basically alpha, beta and gamma are all equal. Okay, but let us not talk about that. Let us first talk about how many lines are there. Usually I have basically 3 lines. Just go back to our original picture. Okay, one component system, I have 3 lines. So what are those lines? One is basically alpha is equilibrium with beta, one is beta is equilibrium with alpha, something like that. Okay, and there is a gamma that way. Okay. Yeah.
So when we talk about mole fraction,
Right.
so we are talking about all the phases, right?
Right.
So, but here you are equating like all the components in one phase, and you are equating that mole fraction to one.
Right.
Shouldn't it be like addition of all the mole fraction in all the phases should be equal to one?
It is your definition, right? Basically, for a single phase, okay, like we did the other day in solution, right? So, what is the mole fraction of water versus salt? Not in the vapor. So, for a particular phase, we are talking about mole fraction. Because you can always say this, like I have this many moles of water and this many moles of the salt in the solution, okay? So I'll just get the mole fractions right away. Okay. What you are saying is also correct. You are saying basically the total amount of a given substance will be same in all the phases, will be basically added up. Okay. But that is not exactly a fraction. Think about it. Because that will depend on what are the equilibrium conditions. Right. But at a given pressure and temperature, I can look at it in a different way for a given phase. What are the mole fraction for different components? Mole fraction comes from different components, not for one component in different. Think about it. Like it's not a one component for different phase. It's different component in the same phase. Okay. All right. Now the second thing is that suppose I have an equation for alpha, beta. Okay. And let's say I'm saying some textbook actually write it. That's why I'm writing it something like that. Okay. Now when I write it like this, actually this is not like 3 equations or like these are not connected. It is basically 2 equations. One is alpha is equal to beta and beta is equal to gamma, something like that. Okay, when the phases are in equilibrium. Okay, meaning this is basically talking about 2 different lines. Okay, some textbook actually write it in this way. Okay, which is not a very like good way of writing. Okay, so what I'm saying, when alpha and beta are in equilibrium, okay, I have an equation. Okay, when beta and gamma are in equilibrium, I have some equation like this. Something like that. Clear? Okay. So basically the chemical potentials are equal. Now how many equations I am getting? Think about it. Actually if I have p phases, okay, how many equations I am getting? Huh? Like in this case actually I have 2 equations, right? So yeah, but what I am trying to say is that no, I am getting 2 equations, right? I have basically 3 phases. Okay. So basically what I am saying is that I have p minus 1 equations, right? Okay, because I had alpha, beta and gamma. So what I am saying is that if I'll also get an equilibrium condition. Equilibrium condition means chemical potential in the 3 phases are equal. Okay, mu alpha is equal to mu beta is equal to mu gamma. Okay, for each component, by the way. So for one component, actually I am getting basically 2 equations. Okay, something is equal to something is equal to something means actually you have 2 equations. Okay, I could have written it as this. So I basically have p minus 1 equations, okay, for each component. How many components we have? C components. So I have basically C times p minus 1 equations, okay, which are coming from the phase equilibrium. Clear? Okay. So I have in addition these 2 things. Okay, now I am done. Okay, so these are the number of equations I have. This already, again, this is the same, like if I have a single component system, okay, and then I can always show mu alpha equal to mu beta and then I can start deriving the Clausius-Clapeyron equation. Same thing, okay. Similarly, the other line, equation for the other line also I can draw, okay. So the same way, I have basically p minus 1 equation for each component, okay, meaning that time we only consider one component system which has water or carbon dioxide. Now I suppose I have water and phenol, so I'll have a water equation 2, I'll also have phenol equations 2, okay, because there are 2 components. So now I have total is this, okay, again this p was coming for the mole fraction for each component, sorry, mole fraction of different components, okay, in the same phase. So there are p phases. Okay. So all I have to do now to subtract. Okay, these 2. So basically the number of degrees of freedom is 2 plus Cp minus p plus Cp minus C. The Cp thing will cancel. Okay. So what I will have is basically p minus C plus 2. Okay. So this is a very compact notation, okay, which is given by Willard Gibbs, and this is usually known as the phase rule. Okay, the phase rule means actually basically is connecting how many, okay, degrees or independent variables you need to describe, okay, your phases. Yeah.
It's C minus P plus 2.
Oh, sorry. This P is minus, right? So basically I'm taking minus of this. Okay. Now just quickly think about it. That's a good question actually. Why C should be minus or P should be minus? If I increase the number of phases, think about it. Degrees of freedom will be less. Why? Because each phase, if I add, that will add one equilibrium condition. So one extra equation I'm getting. But if I am adding C components, I'll have an increase in variable. So C enters in this equation as a positive quantity, P enters as a negative quantity. Okay, alright. And this 2 is coming in from the fundamental pressure temperature. Okay, those 2 things. Quickly check the very first example, but we showed it in a different way, like water. Okay, I showed you like if I have like bulk phase, okay, only one phase, then I have 2 degrees of freedom, pressure, temperature. If I have 2 phases in equilibrium, I had one line, which was 1, and we got something like 3 minus p. Okay, but this is a general equation. Okay, if C is equal to 1, meaning only one component, okay, so you have 1 plus 2 is 3, 3 minus p. Okay, that's what was the 3 minus p, which we got. Okay, now the interesting thing is, whenever we write or whenever we draw a phase diagram, okay, now think about it, one component, I have 2 variables, okay, which we already said, okay, it is 3 minus p, and then if I want to, let's say, talk about maximum, I have what? Maximum I have, okay, so let me just say one component. I have basically 3 minus p. Now if you are considering only 1p means one phase. Just I am asking, okay, how many variables you need to draw the behavior, I mean how many intensity variables you need for say water when it is in the vapor phase, fixed, P is 1, you need 2. 3 minus 1 is basically 2, which are pressure versus temperature. Okay, or you can have pressure, volume, pressure, that is your original choice. Okay, or volume, whatever. Like I can draw Boyle's law, I can draw Charles' law, whatever. Okay, now I am asking, making it a little bit complicated, that what are the number of variables you need for water when water is in equilibrium, liquid water is in equilibrium with ice. Then you are saying, okay, actually there are 2 phases. Okay, this is 3 minus 2, that is only 1. Because that's a line. A line means actually once I have varying the pressure, the temperature is fixed, or the other way. If I am varying the temperature, pressure is fixed. Okay. Similarly, if I just asked what are the number of variables if water, okay, for water, okay, all the 3 phases are in equilibrium, which is a triple point, which is a very unique value. So there is no degree of freedom. So it is 3 minus 3 equal to 0. That is the meaning. However, if you can see the complication, if I actually have, so the meaning is that the maximum number of degrees of freedom here is 2. So I can plot the phase diagram on a 2-dimensional plot for a pure component system. Moment I have water and phenol, I cannot actually, because its third axis is also there. Okay, and then the plot will not be a line plot, it will be a surface plot. Okay, then you have to consider like take more constant, like what the 2 surfaces are crossing. Okay, what is the equation of line for that thing? So all these complications will come. Okay, so or we have to take projections on a particular plane, something like that. Okay, because the degrees of freedom are increasing. Particularly it will increase with components because C comes as a positive number. Okay, if I had more phases, then it will be more less actually. Okay, all right.